Hello everyone. Today I wanted to prove this theorem in abstract algebra regarding rings. So the theorem is, if you have a commutative ring with unity 1, and if that ring only has two ideals, then it must be a field. In order to prove this, first let us examine the properties given here. So in order to show that R is a field, we have to show that since we have unity, we have to show, what we have to show is for all non-zero element in R, then X inverse is in R. So this is what we want to show. And then for that purpose, we'll take a non-zero element first. Let X be an element in R. And then we are going to create an ideal XR, which is defined to be basically you just multiply X to every element in R. And we are not going to prove this here, but as an exercise, we can prove that this is ideal. This is an ideal. So, since XR is an ideal, and then we only have two ideals here, as shown, as given in the problem. So this XR must be one of the two ideals. And then for any ring, the not empty set, the set with 0 and 1 is and itself. Well, actually not 0, 1. 0 and itself are ideals. And this is pretty clear, because each of them is obviously a group under addition, and then they are both closed. They both absorb the elements, because for 0, if you multiply anything, everything turns into 0, and then for itself, well, that's obviously true. So that means XR has to be either 0 or XR equals R. And then this is impossible, because 1 is in R as given here in the problem statement, which means X is in R. But we said that X is not at 0. Oh, sorry. XR. X is in XR. And then X is not at 0. So that means XR cannot be a set that only consists of a 0. So that means this case is not possible. So it must be this. Then 1 is in R, which is equal to XR. That means there exists Y in R such that XY was 1. This is because we created XR to be a set where you just multiply every element by X from the left. And then this is really just the definition that, the condition that we discussed here. So we found the multiplicative inverse of x. And then this x was, this is an argument that you can apply to every non-zero element in R, which means every non-zero element in R has inverse under multiplication. So R must be a field. And that is the end of this proof. Thank you very much for watching.